I start talking. Recording in progress.
Okay, so we're very pleased indeed to have Jose. He's going to talk about Klein, arithmetic, Fuchsian, and Kleinian groups and knots.
Well, this is going to be a melange of talks and something that I have added today because I have done some progress recently, and this talk, the talks that I have prepared do not contain all the information. So I will start with this talk that I gave in Aveiro in September of 2011. Let's see. If I put presentation, if I put this, you can still see this?
Yeah, that's fine.
And these two?
Yeah.
Well, let's make a bit of history. The so-called Clifford-Klein problem. We consider the Beltrami model of hyperbolic geometry, which is this is the first model of hyperbolic geometry. And with this model, Beltrami was able to prove that the hyperbolic geometry was consistent relative to Euclidean geometry. It's the interior of a triball of radius 1. So it's the set of points, this is the set of points of hyperbolic geometry of dimension 3. The chords, so you have to imagine this ball of radius 1. The chords are the straight lines in this geometry. The chords without the end points of the chords, which are points at infinity. With this, the projective geometry becomes consistent with respect to or relative to Euclidean geometry. Now we talk about the Klein model of a hyperbolic geometry. It's a little variation of Beltrami model. We consider something more general than a ball. We consider the interior of a quadratic Q of Sylvester signature minus, plus, plus, plus. For instance, a matrix, the matrix, the diagonal matrix menos 1, 1, perdón, it's in Spanish, minus 1, 1, 1, 1, is the set of points of three-dimensional geometry. This is the interior of the three-dimensional ball. But if you have minus 1, 2, 3, 7, well, then this is an ellipsoid with different axes. But the interior is still a model of the hyperbolic three-dimensional geometry. It is very convenient to work with this model because all hyperbolic geometry becomes a part of linear algebra. And the best source to understand this, and I recommend very much, are the talks by William Thurston that he gave in Princeton in the year 76, 78. And I was fortunate enough to learn all this from Thurston. And I give my thanks to him because he was a wonderful teacher. The chords of this ellipsoid are the straight lines, and the group of isometries is the set of collineations of the projective 3 space fixing globally the quadratic. Remember that collineation, also called projectivity or projective transformation, is in the underlying topological vectorial space of dimension 4, R4, is just an automorphism. So, in fact, a collineation, geometrically speaking, is a one-to-one map of RP3 sending lines to lines. This is a collineation. And one of the main theorems of projective geometry is to prove that such a thing comes from an automorphism of the underlying vectorial space. If the matrix of the quadratic form for Q is the 4x4 matrix F of Sylvester's signature minus plus plus plus, for instance, imagine that is minus 1, 2, 3, 4 diagonal. Then the quotient, this quotient, xt is an horizontal vector. You can imagine that this is the vector 1, 3, 4, 5. And y is a vertical vector, 7, 8, 9, 10. And f is the matrix. So this is, in fact, the scalar product of the vector x with the vector y by means of the symmetric matrix F. And then you divide this by the square root of xt fx, which is the square root of the norm of the vector x, times the square root of the same thing with the vector y. This quotient probably recalls you of the formula of the cosine of an angle. If f were a quadratic form of the type plus, 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 for instance, 1, 1, 1, 1, then it would be, the quadratic form would be a sphere. That would be what we know perfectly well from spherical geometry. But here the form F is not definite, it's indefinite. And according to the position of the vectors x and y with respect to the quadric, then this quantity, this quotient of numbers, has different interpretations. And this is one of the main ideas explained by Thurston in his notes. For instance, if the vectors x and y are points, correspond to points x and y inside the quadric, so in fact they are called 2 points of the hyperbolic space at finite distance, then that formula gives the hyperbolic cosine of the hyperbolic distance between these 2 points. But if the points x and y are outside the quadric, so we say they are in the ultra infinite, then these 2 points have respective polar planes. How to obtain the polar plane of a point outside a quadric? You take the cone, the tangent cone with apex, the vertex, the point x, and tangent to the quadric. And this tangent occurs along a conic. The conic lies in a plane, and that plane, in fact, is the polar plane. When you have 2 points in ultra infinity, then they have 2 polar planes. Well, the hyperbolic cosine of these 2 polar planes are given by the same formula. Everything becomes very useful for using computers. And I use these formulas in my computing all this geometry. If one point and similar things, but that I don't want to confuse you with many definitions. So it's enough what I have said. Comments. Klein in 1971 drew the idea of the model from Cayley's paper. The paper by Cayley was called A Sixth Memoir upon Quantics, 1859, and illustrates his famous assertion that the subject of any geometry is the study of geometric properties which are invariant under the transformations belonging to some transformation group. the paper by Cayley, 6 Memoria upon Quantics, is very interesting. There is a previous paper by Cayley in which, in fact, he defines the geometries associated with quadrics. So he, in fact, knew everything. And in a different paper, he read Lobachevsky. And that paper of Cayley is incredibly intelligent. You should read it. Also, Cayley, in fact, has all the elements to create this Klein model much earlier than Klein, but he didn't. So Klein made the Beltrami model more flexible because the quadratic form F is very general. It can represent an ellipsoid, even a paraboloid, not hyperbolic paraboloid, a paraboloid, so something like rotating a parabola, or a two-sheeted hyperboloid in a fine space. Because in hyperbolic space, all these quadrics bound a three-dimensional ball. The hyperbolic paraboloid bounds a solid torus. So the group of isometries in this case is the set of 4x4 matrices T, real matrices T, such that T transpose Ft equals F. So in fact, the transformations that fix the quadratic form. So leave invariant the hyperboloid or the quadric, say. But this group of isometries is a Lie group, is the group of isometries that preserve the orientation of the hyperbolic place. Is a Lie group, but sometimes it contains discrete groups, so-called discontinuous groups of isometries of H3. And this is the origin of hyperbolic manifolds, hyperbolic orbifolds, and arithmetic groups comes from here. So let's say that a subgroup H of the group of isometries of H3, of, say, orientation preserving isometries, is discontinuous if it acts in H3 in such a way that the quotient topological space by the action, which is the so-called Clifford-Klein form, is a three-manifold, or more generally a three-orbifold. That the other day we were talking about, in this case, three pseudo-manifolds with some special types of singularities. Remember what I said in my last talk. There are some singularities. In this case, the singularities form a graph that can contain isolated points. The singular points are points whose star length is the projective plane. So is the neighborhood of this point is a cone of the projective plane, or mirror planes in the topological boundary. If we allow isometries that reverse the orientation, in these two cases, the group contains transformations that reverse the orientation. The intersection of two of these are edges. So imagine that the quotient orbifold is a tetrahedron. For instance, it can be a tetrahedron. A tetrahedron contains vertices and edges. In the edges, the angle is pi over an integer. An intersection of three of these correspond to vertices of the tetrahedron. They must be marked 2, 2p, 2, 3, 3, 2, 3, 4, or 2, 3, 5. Why? Because the regular neighborhood of one of these vertices is a cone over a hyperbolic, over a spherical orbifold. And the only spherical orbifolds are those with Euler characteristic positive. As I said in my last talk, 2, 2p, 2, 3, 3, 2, 3, 4, 2, 3, 5 correspond to spherical triangles, you see, of angles pi over 2, pi over 2, pi over p, or pi over 2, pi over 3, pi over 3, pi over 2, pi over 3, pi over 4, and 2, 3, 5. All these are the possible spherical triangles with angles of the form pi over an integer. And also, the singularities contain orientable two-fold covers of those, namely edges with edges inside the orbifold, in the interior, not in the boundary. For instance, it could be some edge connecting one vertex of the tetrahedron with the barycenter of the opposite face. That thing could be an edge with an angle of the form 2 pi over an integer. And incident points of 3 edges must be of this form. Also, orbifolds, which are, in this case, not a spherical triangle, but the doubles of a spherical triangle. So pillows, they are pillows of 2, 3, 3 angles, P2, P3, P2, P2, 3, 2P over 3, 2P over 3, etc. Do Clifford-Klein forms really exist? This is the context of the famous Clifford-Klein problem. The problem is, find all the Clifford-Klein forms which are geodesically complete and with finite volume. There is a book in Italian, very old, about hyperbolic geometry, in which this problem is clearly stated and is attributed to Clifford and Klein. Well, who was the master of this problem? William Thurston. William Thurston was able to show that almost all manifolds and almost all knots correspond to Clifford-Klein forms. I am going to give you an example, concrete examples that you can understand, because I didn't put many pictures, I'm sorry. And perhaps it was very abstract and arid, but please, I will put an example. This example is taken from the works of Luigi Bianchi, at least only the origin, the beginning of the example. The rest of the example is in part due to Thurston and my colleagues, Maite Lozano and Mike Hilden and I. The first example is the so-called Picard group. This is one of the first discrete groups of isometries in the hyperbolic space. Picard is a French mathematician, essentially discovered that the group of 4x4 matrices with integer coefficients such that preserve the form F T transpose F T equal F, where F is the diagonal quadratic forms minus 1, 1, 1, 1, so is the sphere, is the two-dimensional sphere. The hyperbolic space is inside this spherical, this sphere, for radius 1. This group of matrices, of integral matrices, act in H3, in the interior of the ball, by collineations, by projective transformations, fixing the boundary. And the quotient space of the axiom is a Clifford-Klein form. What is the Clifford-Klein form in this particular case? It's a tetrahedron. The quotient space is a tetrahedron, which is this tetrahedron that you see in the picture with solid lines. You see a big tetrahedron, or something like that, which has vertices 0, 0, 1, 0, 0, 1. This means that these are homogeneous coordinates. So to take the affine coordinates, you have to divide all the coordinates by the last one. So the vertices in the affine space are 1, 0, 0, 0, 0, 0, which is the origin, 0, 1, 0, and 0, 0, 1. All belong to the two-dimensional sphere of radius 1. And these 4 points produce a tetrahedron, the big tetrahedron. The solid tetrahedron is what you see inside. if you compute the angles using the formulas that I said before, you obtain what you see there. You see that there are solid lines marked pi/4, which is the one at the how to say, in the background, is a pointed line. And there is another edge to the left, which is marked pi/4. And one connecting the vertex 0, 0, 0, 1 with the barycenter of the opposite face, which is marked pi/3. The remaining edges should be marked pi/2. So this is a tetrahedron in which, for instance, imagine, look at the vertex 0, 0, 0, 1 on top, the one which is on top. To that vertex, inside, 3 edges, pi/4, pi/4, and pi/2. Remember the other day in my talk of the Alhambra, or the Alcázar de Sevilla, I considered an Euclidean orbifold corresponding to the triangle with angles pi/2, pi/4, and pi/4. This is a Euclidean triangle. It's an isosceles right triangle, no? It's Euclidean. Why this triangle is Euclidean? Because the point 0, 0, 1, 1, it's at infinity. It's at infinity. And Gauss, Bolyai, and Lobachevsky knew very well that the geometry of the radiation coming from a point at infinity in hyperbolic space has the geometry which is called equiform geometry. Is the Euclidean geometry plus similarities. But if you take a little sphere center in 0, 0, 1, 1, that little sphere has its center in the sphere itself. Is the so-called is a so-called horosphere. Is a horosphere. So the geometry of the horosphere is Euclidean. This is one of the main discoveries of Gauss, Bolyai, and Lobachevsky. It's Euclidean. Therefore, when this horosphere cuts the orbifold, this horosphere cuts a triangle in the horosphere, which is Euclidean, and that angle and has angles pi/2, pi/4, and pi/4. This is very, very beautiful. Now look at the point at the vertex 0, 0, 0, 1, which is exactly down. This point, and in this point, you have 3 edges, pi/3, pi/4, and pi/2. 2, 3, 4. This is a spherical triangle. Why is this? Because this point is inside. It's a finite point in the hyperbolic space. It's not at infinity. It's inside. So the radiation coming from this point has the spherical geometry. And a little sphere around that point cuts the orbifold in a spherical triangle. The spherical triangle pi/3, pi/2, pi/4. And similarly, if you look at the other vertexes, you will see that all of them are also spherical. Only one is Euclidean, corresponding to the point at infinity. Well, this tetrahedron is the fundamental domain of the action of the group of integral matrices in H3. Is the fundamental domain. And the action in H3 has a quotient as a quotient has this orbifold. Now it's an orbifold. It's a tetrahedron, but the faces of the tetrahedron are mirrors. And the edges of the tetrahedron correspond to corner singularities. Yes. Here downstairs, you can see the point, what I have written, it's a cuspidal point because it is placed at infinity. The three edges coming to it are marked 2, 4, 4. This means that the sphere center there is a sphere which is singular because the center of the sphere lies on the sphere. That's the reason it's called a whole sphere. Cuts orthogonally these three edges, and its intersection with the orbifold is a Euclidean isosceles right triangle. Now, even if P, if this tetrahedron is not compact, because it has a point at infinity, it's not compact, but is complete. That is complete in all senses of completion. In the Cauchy sense that all Cauchy sequences have a limit, and also the sense of geodesically complete, because all geodesics can be extended infinitely, because the end of the geodesic is at that point at infinity, which is at infinity. So the geodesic can be extended, is geodesically complete and metrically complete with any metric which is compatible with the group of isometries. And the volume is possible to compute is this number. And I have a program that allows me to compute the volumes of all these hyperbolic orbifolds. I take a quadratic form. I consider the group of all integral matrices. I made this group act in H3, and I compute the orbifold, the quotient orbifold. I compute also the volume and everything. It's a program that I have made starting in 2009, and it took me some years to do. No publish. The fundamental group of the orbifold can be computed by generators and relations, just exactly as you do with a manifold. In a manifold, you know the manifold, you can give a presentation. You have an orbifold, you can do the same. And then you can find a faithful representation of this group of the orbifold by matrices of the group, which are integral matrices. Now, the method to obtain this orbifold, this Krivol-Krine form, is a arithmetic method. It's taking matrices with integral entries. And this is the origin of arithmetic groups. This method can be applied mutatis mutandis to any integral quadratic form producing the arithmetic Clifford-Klein form defined of the rational field, Q, the rationals, but can be generalized to any number field, which has some properties, given the general theory of Clifford-Klein forms. It can be understood using the theory of generalized quaternions. Now, the relationship between this theory of matrices with integral entries and quadratic and generalized quaternions has been obscured with time, so that not many people know why these quaternions appear. If I have time, I don't know if it is going to be before the summer or after summer. I can give you why this generalized quaternions appear. They appear in the work of Hermite. Hermite was the first that found quaternions, probably independently of Hamilton. And they appear in the study of ternary quadratic forms. And I use them very much in my research. Now, how knots and links appear in this context? Well, it turns out that certain covariants of some non-compact Clifford-Klein forms are the complements of some knots and links. I hear somebody talking. Well, and more important, almost all knots and links, the so-called simple knots and links, are the singular sets of suitable compact Clifford-Klein forms. This is the work of Thurston. And since according to a celebrated theorem of Mostov, the manifold of dimension 3 admits at most a unique structure of Clifford-Klein form. So if it is hyperbolic, the hyperbolic structure is unique. So all the metric invariants are at the same time topological invariants. So Maite and I, we have studied the volume, the Chern-Simon invariants. We have computed this, fine formulas, Slaffly type formulas for the volume and for the Chern-Simon invariants, many papers. And they can be computed giving topological information on knots, links, three manifolds, and three orbitals at the same time. For instance, this Picard orbifold has a 96 sheeted orbifold covering, which is the exterior of the Borromean rings. So the Borromean rings, the exterior of the Borromean rings at infinity, they disappear from your point of view. The Borromean rings has a complement, which is hyperbolic, of finite volume, complete finite volume, and the volume is 96 times the volume of the tetrahedron. I am going to show you how this happens. Just consider this octant composed by by 6 reflections of Picard orbifold. So you take the Picard orbifold and you make these reflections. You have 6 of these tetrahedra. And then with 8 octants of what I have just obtained, you get an octahedron. So the 8 octants times the 6 tetrahedra are 48 copies of the Picard orbifold. So you have a map from the octahedron to the tetrahedron, which is 48 to 1. But the octahedron has 6 cuspidal points. In particular, we can tessellate the hyperbolic space by replicas of this octahedron, which is in fact a theorem of Bianchi. Now, if you imagine the octahedron at the left, top left, and you consider the barycenter of the octahedron. From this barycenter, you can divide the octahedron, taking the cones with apex, the barycenter, and base the 8 faces of the octahedron. So you have divided the octahedron in 8 parts with the same apex, which is in the barycenter. Now you reflect all these 8 parts in the faces of the octahedron. So what you obtain is that on top of each face, you have now some pyramid. The addition of these pyramids is a rhombododecaedron. That one that I see there. What is a rhombododecaedron? Is just you put some pyramids on top of a cube in such a way that the new faces produce a body which has only 12 faces. This is a rhombododecaedron. And now you see in a rhombododecaedron there are 2 types of vertices. There are vertices which are marked infinity, to which 4 edges touch, and there are edges which are the vertices of the original cube, to which 3 edges meet. The ones that comes from the cube disappear because they are containing the faces, in the new faces. So in fact, I think I have a copy of, let's see. Now, if we identify in pairs the faces of the rhomboidecahedron, as is explained in the picture to the right, you see that I am identifying using the, I mark the identification with some sort of arc with the, so that gives you the idea of the identification of the faces. If you make this identification, we get the exterior of the Borromean rings in the 3-dimensional sphere. This is slightly difficult to see, but let's do this in the reverse order, and you will see that in fact it's true. This was done in I learned this in a talk by Thurston in Princeton many years ago. So you start with the Borromean rings, and these Borromean rings bound 3 interlocking cards. We think of each of them made of 2 discs of rubber pasted together along the boundary. So you have to think that these cards are made of rubber, so you can inflate what is inside. You put some sort of tube and you put air, and this thing starts growing up. What happens? What happens is that you get that look, the triple point in which the 3 interlocking cards meet, that triple point, when you inflate, gives the 8 vertices of this cube. Now, so you blow up and inflate to get a bubble, outside of it is the matter, and inside is air. And now reflect the boundary of the bubble to get the matter inside the bubble and the air outside. Now you have, I say again, take the 3 interlocking cards, which are made of rubber, and then you blow air, and then inflates, and the point in the center produces the 8 vertices that you see there, and these gross lines correspond to the Borromean rings. You need some sort of imagination to realize that this is true. And then you see here that since we are trying to understand the complement of the Borromean rings, you have to collapse the solid lines which correspond to the Borromean rings. These Borromean rings go to points at infinity, are the cuspidal points. So you have to imagine that the Borromean rings are going away and away and away to infinity, and then when they reach infinity, they disappear from your point of view. So to obtain the complement of the Borromean rings in the hyperbolic space, you have to collapse the solid lines into points. And collapsing the top line, you obtain this vertex. Collapsing this line, you obtain this vertex. And collapsing this, you obtain this vertex. And there are other solid lines in the back. So in fact, the complement of the Borromean rings is this 96 to 1 covering of the Picard orbifold. In other words, there is a subgroup of integral matrices that acts in the hyperbolic space and has as a quotient orbifold the complement of the Borromean rings. So the Borromean rings are hyperbolic. And the volume is 96 times the volume of the tetrahedron, which is that number 73277. This is a topological invariant. You have another hyperbolic not only with a different volume, that means that they are different. But in fact, there are links that have the same volume. But sometimes they have differential Simon invariants. So this number is a topological invariant. The conclusion is that the discovery of Gauss, Bolojai, and Lobachevsky of H3, the Beltramis model and Cayley geometry gave Klein the idea of placing H3 as an example of his Erlanger program. The studies of Fricke and Klein on the so-called Fuchsian groups, which are the ones producing two-dimensional Clifford-Klein forms, gave origin to the problem of Klein of finding all the possible Clifford-Klein forms. And the construction of Picard gave origin to the so-called arithmetic method to obtain examples of Clifford-Klein forms. To this contributed Fricke, Klein, Dick, Bianchi, and many others in beautiful papers that you can find in the German journals of the time, especially in the Mathematicianalen, and also in the Italian journals of the time by Bianchi, which was a professor at the celebrated University of Pisa. The modern theory of arithmetic groups was developed by Borel and Harris Chandra. And the work of Mostov made clear the topological importance of the Clifford-Klein forms. And definitely the one that understood all this was Thurston. The impressive work of William Thurston put all this together and clarified finally that hyperbolic geometry is all the topology of three manifolds. This is the modern version of the old dictum. Projective geometry is all of the geometry, to which so much we are indebted to Felix Klein. So now let me try to ¿cómo se podría? Escape. Aha. I close this and I go to a different talk. Sharing has stopped. Okay, and then I have to share a screen. And I go to not here. Oh, sí. Aquí. Aquí. Oh, sorry. How to share? You are. Can you see this?
We can see your screen, Jose, but you need to click on what it is you want us to see.
See, you are screen shading. Stop. New share. New share is this. Share. Can you see this?
Yes, we can see that now. Yeah.
Which is was a talk that I gave in Zaragoza in honor of Maite Lozano that retired. She is still doing mathematics with me.
Right.
Well, it was called integral quadratic forms and the associated orbifolds. And we have binary quadratic forms. And I would like to talk after this a little bit about binary, because binary gives you the main problems. And these problems were solved already by Gauss and others many years ago.
I mean, Jose, if you want, if there's another talk here, you can give it at some other occasion.
It's already time to finish.
Well, no, I'm just thinking of people maybe have to go at 6.
Probably people is tired. No, I am tired. It's 7 o'clock.
Yeah.
Okay, so let's do this next day.
Yeah, that would be great. Yeah. Shall we do it next week?
See, let me show you some of the pictures.
Okay, let's see some pictures.
Some pictures to explain. I can do pictures by hand, but not by computer.
No, they're beautiful.
You see, this is the one that I took me a lot of time, which is to understand quadratic forms with signature plus plus minus minus. Then you get a hyperboloid. This is a rule hyperboloid. And the hyperboloid has two rules, to the right and rules to the left. The set of rules to the right and to the left correspond to the product of two hyperbolic planes. So the orbifold is four-dimensional. It's the quotient of two hyperbolic planes by the action of a group. And I studied this group of automorphs. And there are many things to be done here. So people can continue my research on this paper that was published in some journal. And here are the problems. I continue the work of Mennike. Mennike was one of the great people doing this in early times. Orbifold coverings. This is a common covering, which shows that these two orbifolds are commensurable. And then I give invariants of commensurability using the work of John Horton Conway, who died last year. And the invariants are, I will try to show you the invariants, because I have changed the invariants of Conway and have introduced a new set of invariants that are very convenient to work. And I have solved the old problem of Meyer. The problem of Meyer was to find if some genera of forms have only one form. And this problem I have solved completely with my new invariants. But I will show you some of them. So I finish with that, Roger.
Thank you, Jose, because I think there is some important stuff there which we want to study afresh, yeah?
Yeah, and I prefer to do this slowly.
Yeah.
Because there is a lot of information that is very easy to understand, but it has to be done. If people is not used to this geometry, then we'll find this difficult at the beginning. It's what happens to me when I was attending Thurston talks. At that time, I knew a lot of projective geometry from my studies at Madrid, but the way that Thurston put the things was so beautiful that in fact I learned a lot, and I decided to understand it all my life. I have been doing this.
Well, as Hardy said, there is no permanent place in mathematics.
Exactly. Okay, Roger.
Okay, are there any questions?
There would be.
I have a question. Okay, here is a rhombic
put it. See, yes. yes. Yeah.
Now, the four-dimensional version of this is a three-dimensional object. Four-dimensional version, the vertices are the units of the ring of
you take the 27.
Hurwitz ring.
Hurwitz ring. And they are also solutions to the Yang-Baxter equations.
Well, so
there is some beautiful mathematics there, but I don't know how relevant that is to your work. Well, but we should talk about it sometime.
Well, that object is a four-dimensional one, no? What you are talking about, the 20 cell?
It's the 26, the 24 cell. Yeah.
Exactly, 24 cell, which is central symmetric. No? Yeah. No, which is not. Let's see. In 4 dimensions, you have the tetrahedron, which is not central symmetric, and this cell, the 24 cell, which is not central symmetric. Or I am mistaken.
Well, the symmetries is the binary tetrahedral group.
You take the tesseract, and then you take in the eight faces of the tesseract.
Take a cone on each face.
And then you take cones over the faces of the tesseract. I think that is the idea. No? And then you have 8 times 3, 24. Why 3? Because you have to take 8 times 6, which is 48. But two of these cones meet together and produce a new cell, which is an octahedron. So you have 48 divided by 2, 24 octahedra. And this is the 24 cell. And the quaternionic group, the group of quaternions, acts in the 3-dimensional sphere. And then it gives the tesseract, I guess. And the fundamental domain of this action, which are 8, the group has 8 elements. And then they have 8 fundamental domains, which are cubes. And the action identifies the face of one cube with the opposite one by 90 degrees. And that gives the 3-dimensional quaternionic space. So the 3-dimensional quaternionic space is a spherical manifold, has no singularities. This is an example of an orbifold. And the same happens with the binary cosihedral group. You have two rings, one ring of dodecahedra. You take 10 dodecahedra, forming a ring. You paste on top of a dodecahedron another dodecahedron, and you do that making a ring with 10 dodecahedra. And then you have spaces between the faces of the ring. And then you place there new dodecahedra. Since there are 10 by 60, you get 10 plus, how many are? Well, in total, there are 60. Each ring contains 60 dodecahedra. With a nucleus of 10 dodecahedra. And they are surrounded by dodecahedra, giving 60 dodecahedra. And then you take the Hopf link and paste these two rings together, and this gives you the 120 cell of dodecahedra. And in there you can see the action of the binary cosihedral group, identifying opposite faces of a dodecahedron by 2 pi, I don't remember now, 2 pi over 5. And then you get the Poincare manifold. Also, this is a spherical manifold, and so on. But there are more groups. And these groups come from the tables of crystallography, 4-dimensional crystallography. The elements of the group that fix a point are subgroups of O4, of the orthogonal group of 4 elements. And they can be defined by matrices, integral matrices in some quadratic form. And this gives you a lot of hyperbolic spherical orbifolds. And I have the total list done. There are 210, I don't know. There are many. I have them in one of my notebooks. And you obtain notes and links. And it's fascinating, which are also spherical. Well, instead of this, you take the hyperbolic space, you get also notes, but in this case, they are hyperbolic. And then you get graphs and theta curves. And it's a fascinating work. In my book, in the book I wrote many years ago, there are these constructions, but I almost forgot everything. I'm forgetting almost everything.
Well,
well, we are all.
it's the same. Anyway, Jose, before you forget anything, you will talk next week.
You want me to talk next week?
Yeah.
All right. Yeah. See, if I talk at this pace, I'm not very fatigued.
Yeah.
No, giving talks is tidy.
There's plenty of time.
Hey, Lou, how are you?
I'm good.
Well, I'm very happy being you and talking to you. It's incredible. We know a lot of mathematics between us. You know, Jan Baxter equation that I don't have the faintest idea. One cannot.
Third Riemannian rule.
Look, one of your papers with Deborah Goldman on the twin of the twist spinning. No, I don't know if you remember that paper. Twist span knots was one of the beautiful pieces of geometry. I enjoyed that paper enormously. You don't remember the paper. You wrote a paper on twist spinning, giving a new interpretation many years ago, and that was wonderful. Maybe I would like to talk someday about something that I found, that you can twist spinning a string, so a Y knot with only one Y point. In twist spinning such a thing twice, you get a two knot in four space, in four sphere, which has a one Y point.
Which has a what point?
A Y point. And it's a fiber two knot, but the fiber is...
Oh, wild knots. It reminds me, I had a question for you. Sorry, this is an important question for me, and maybe you know the answer. I have always wondered whether there is an elementary proof that if you have two classical tame knots that are equivalent in the wild category, then they're equivalent in the tame category.
In the tame?
I have two ordinary classical knots.
Ordinary classical knots.
Not in three space. One-dimensional knot in three space.
Yeah, no, a typical one. Tame.
Tame. But suppose that you know that they're equivalent in the topological category. Then you should know that they're equivalent in the tame category. There should be an elementary proof of that.
But hang on, I mean, you can pull it tight in the topological category. I mean, you're presumably...
No. I mean, I'm talking about topological equivalence of knots, not topological isotopy. I'm talking about being thrown by homeomorphism of space to the other.
One to the other, yes.
Oh, okay.
Right.
But, yeah.
Well,
by an orientation preserving homeomorphism of space to the other.
There are two closed sets in the string, which are disjoint, and then you have an homeomorphism of the string that sends ones to the other. This is called topologically equal. And then you want to prove that in fact if they are tame.
If they're given to be tame, but they happen to be known to be equivalent in the topological category,
yes,
then you should know that they're tame equivalent.
Exactly. And then you want to prove that.
I mean, I'm sure it's in the work of Moïse, but I'm wondering if there's this is a pedagogical question. Could we get it into an elementary book?
We have to define tame. Tame means that there is a neighborhood which is a solid torus, no? This is one definition. We take the definition that the regular neighborhood, so assume the knot is differential, then it has a tubular neighborhood. Assume the knot is piecewise, and then you have a regular neighborhood, and this is a solid torus, no? And by using the definition, you have to prove that if they are topologically equal, then one solid torus goes inside the other solid torus, and you can push one over the other somehow. And I don't know more. I have to think, of course. But in fact, the proof is not going to be easy. And you know that, of course. Well, in fact, a while knot with a point, with a while point, has no such a regular neighborhoods. But if you take the point out, then you get what I call a string in R3. You get a string, which is a closed set, which is homeomorphic to the real line. So the ends of the real line go to infinity. This is a string. Now, if you twist the a string, then you get a string of dimension 2 in R4. And this string, if I take the string wisely, then, and you twist spinning, you get a string in R4, which is fibered. And the fiber is the Whitehead manifold. Because I have proved that the Whitehead manifold is a 2-4 branch covering of a while knot. And then you have a 2 knot. You put now the point at infinity, and then you have a while knot with only one while point in S4 in the 4-dimensional sphere, which is fiber. And the fiber is the Whitehead manifold. So in fact, the complement of the knot has all the homotopical properties of the trivial knot. And then you can, and there are some conjectures about knots that are, whose complements are topologically, homotopically equal to the trivial knot. This example gives you many ideas. For instance, is that knot, well, I don't know. The knot is not trivial. The knot is not trivial. It's not the trivial knot. It bounds up the Whitehead manifold contractible. And it's fibered. It's an open book. And the Whitehead manifold has these two an involution. And then when you turn around the Whitehead manifold, it comes back with this involution. There are also knots.
I think we're going to have a private conversation about this whole thing. Yeah.
No, well, look, I don't know. Anyway. As a matter of fact, the one that can answer this question is Fico González Acuña in Mexico. Ask him. You know Fico. Francisco González Acuña. You know him?
Lou, do you know him?
I'm sorry, what's the name?
Francisco Fico González.
Oh, yes, certainly. Yeah.
It was probably, it was with you at Princeton with Fox. He made his PhD with Fox, probably at your time. And in 1969. And he knows about that. Certainly he can give you an answer.
Mm-hmm.
But it must be.
We'll try talking to him.
It must be in the literature.
Okay, so I guess we'd better stop here. But that was really interesting, Jose.
Sorry, I didn't put pictures. But
oh no, it was great. I mean, I can see that you love the beauty of mathematics.
Yes. Okay, Roger and everybody, many thanks. And to the next, and we see each other next week.
We'll see you next week. Yeah.
Thank you, Jose.
Thank you very much.
Thank you very much. Thank you very much.
Thank you. Yeah.
And Perco.
Yeah.
Ah.
I'm not actually Susan. It's my wife's computer.
I was wondering. Nowadays, you don't know what happens. Okay, goodbye. Then I close the session.
Yeah, we'll stop there now. Okay.
Goodbye then.